Okay, I'm gonna start. Okay, so the FT sequence. Let me present. Okay, so the FT sequence is like you get it's a positive sequence. It's a sequence of positive integers with 2020 terms, and it's called an FT sequence. If each term after the second term is the sum of the previous two terms, so it's like the Fibonacci sequence, but without starting from 0 and 1 all the time. So, for example, if the first two terms were like 7 and 8, 8 and 7, then they'd be 8, 7, 15, which is the sum of 8 and 7, then 22, which is the sum of 7 and 15, and then so on. And then for some positive integer m, there are 2,415 sequences where the first two terms are each less than 2m, and the number of odd valued terms is more than double the amount of even valued terms. So then it's asking you what is the value of m, and then it's a multiple choice question. So there are 5 answers here. So you have 21, 69, 115, 35, and 105. So the solution. There are four sequences possibility like there are four possible sequence combinations for the FT sequence. Sequence one, it starts with odd, odd, even. Sequence two, it's all even. Sequence three, it's odd, even, odd. Sequence four, it's even, odd, and odd. So since the term depends on the parity, which is whether it's even or odd, of the two preceding terms from it, the pattern will just keep repeating until it ends. So yeah, we can just represent it like this. So just a quick, like, before we get started, this is um we don't actually want sequence 2 before we start the investigation, because it's all even numbers, and the requirement was that it needs double the more than double the amount of odd numbers than even numbers. So that means the rest of the sequences 1, 3, and 4 each have their own repeating pattern, and they all meet the requirement of more than double the amount of odd numbers than even numbers. So the pattern, it repeats every 3 terms, so that we know for sequences 1, 3, and 4 that there will be one even number every pattern repeat. So that means if we know how many times the pattern repeats in the sequence, that means we know how many even numbers are in the sequence. And then since the pattern has 3 numbers, we divide the length of the sequence by 3. So sequence 1. So 2020 terms divided by 3 is 273 with a remainder of 1. So we know that sequence 1, 3, and 4 each have 673 even numbers. Since there's only one even number per pattern, um, that means there are 673 even numbers. And the pattern also repeats 673 times. So 2020 is really long, so we're going to use 10 instead. So 10 divided by 3 is 3 with a remainder of 1, same remainder. So in sequence 1, there are 3 patterns with one odd number as the remainder. So in this case, we have 3 even numbers, which is the same amount as the number of patterns. So that means the number of odd numbers is 2 times 3, which is 6. 2 times 3 because there are 2 odd numbers per pattern, and and there are 3 patterns that repeat. So then we add the remaining odd number, which is the last term. So that means there are a total of 7 odd numbers, and 7 is greater than 2 times 3, which is the amount of even numbers. So you can see the last remainder is odd here. So this is sequence 1, and this is not divisible by 3, so it is the remainder. And this is also the term that makes sequence 1 fit the requirements. So since let me show. So you can see this pattern, it repeats 3 times. So here it goes 3 terms, and then it repeats again for another 3 terms. And then after another, it repeats again. But then this one is left out. So this is the remainder. Okay. So do you guys understand so far?
Yeah.
Okay. So since 7 is greater than twice the amount of even numbers, it means it fits the pattern, fits the sequence requirement. So correspondingly, same thing with 2020 terms. There's 2 times 673 plus 1 odd numbers, since there's one odd number that remains because it's still sequence 1. And 2 times 2 times 673 plus 1 odd numbers is greater than 2 times 673 even numbers. So sequence 1 fits the requirements and it's selected. So sequence 3, we already ruled out sequence 2, so we're skipping straight to sequence 3. So same thing, 2020 divided by 3 is 673 with a remainder of 1. So in sequence 3, there are 3 patterns with 1 odd number as the remainder. So let's see the sequence 3 chart. So sequence 3, you can see it's the same thing here. So every 3 terms, it repeats the pattern. And there is one leftover odd number that makes sequence 3 fit the requirement of more than double even and odd numbers. So same thing with sequence 1. There are 7 total odd numbers plus the last one that remains. And 7 is greater than twice the amount of even numbers there are in this sequence. So same thing again, 2020 terms. There are 2 times 673 plus 1 odd numbers. And 2 times 673 odd numbers is greater than double the amount of even numbers in this sequence. So sequence 3 is also selected. So sequence 4, there are 3 patterns with one even number as the remainder. So in this case, we have 4 even numbers because there's one as a remainder this time, which is more than the number of patterns. So you can see here that sequence 4, it does the same thing. It repeats 3 times, but then there's an even number left over this time. So that means there are one more even number than every other sequence, 3 and 1. So that means the odd numbers are not more than double the even numbers this time. Okay. So that means six odd numbers is less than double the amount of even numbers. So when we get to 2020 terms, there are 673 plus 1 even numbers because the even number is the remainder this time. And 2 times 673 odd numbers is less than double the amount of even numbers plus the remainder. So sequence 4 is not selected. So the number of ft sequences in sequence 1's pattern, we know that the parity of the first two numbers, which is again whether it's odd or even, decide the sequence pattern itself. So the combination of the first two numbers will decide how many ft sequences there are in the pattern of sequence 1. So given that the first two numbers are both less than 2m, and considering 2m is an even number, there are m odd numbers and m even numbers in the domain of 1 to 2m. So for the first odd number, there are m choices. And for the second odd number, there are m minus 1 choices because we already picked a choice for the first number. So in total, there are m times n minus 1 number of ft sequences that have the same pattern as sequence 1. So for the number of ft sequences in sequence 3's pattern, so there are m choices for the first odd number, same thing. And for the even number, which is the second term of the sequence, there are also m choices because we didn't pick a choice for an odd number, and we're not picking for an odd number. So in total, there are m times m number of ft sequences that have the same pattern as sequence 3. So to find the total number of ft sequences, we add the two combos. So it's m times m plus m times m minus 1, and that should equal 2,415. So we can change that into a quadratic equation. So there are 2m squared minus m minus 2,415, and that should equal 0. So we can solve for m using this quadratic formula when the equation equals 0, and in this case it does equal 0. So for the solution, finding m is we plug the numbers into m's, like the quadratic formula to find m. So then here, negative b is negative 1. So a negative is a positive, so it's just 1. So we're doing 1 plus the square root of negative 1 squared minus 4 times 2 times 2,415 divided by 2 times 2. So then we can start multiplying the terms with each other. So we get 4 times 2 is 8. So we swap out 4 times 2 for just 8. And then 2 times 2 is also 4. So we swap that out for just the 4 here. So then we get just, negative 1 squared is also just 1, because you should know that negative squared is positive, and 1 times 1 is just 1. So we get 8 times negative 8 times negative 2,415 is 19,320. And this is a positive because we had a negative times a negative. So then we have 1 plus 19,320 is 19,321. So then we get the square root of 19,321. This is 1 plus 139 now, which is 140. 140 divided by 4 is 35. M2, you might notice that this is a plus or minus, so this can be plus and minus. So we did the plus for the logical choice of the positive answer. So M2 is negative 34. And the number of terms, it obviously you can't have a negative number of terms. So we're going to forget about M2. So M equals 35. And if you didn't understand this, there's another alternate solution. You can just plug in each number into the equation until you get the number that gets you exactly 2,415. Okay? And that is the answer.
Somewhat confused.
Yeah, so, oh, by the way, the answer is D. 35. So, any questions if you're confused?
I'm still somewhat confused.
Which part are you confused about?
Like, go back?
Which slide? Where?
The other one.
Tell me when to stop.
This one.
This one? Okay. So what are you confused about on this slide? Oh, m times m minus 1. That's the combination. So if you multiply the two choices, like if, for example, if you're rolling a dice, if you're rolling two dice, then the possible like outcomes of rolling one dice is 6. But if you're rolling two dice, uh, then the possible like combinations is 6 times 6, right?
Oh, okay, I see.
Yeah, so we minus 1 here because they're both, the first two are both odd numbers, and there are a fixed number of choices for this odd number. So once we pick an odd number from 1 to m, then that is already picked, and there's one less choice because we already picked it. So this is m minus 1. Right?
Yeah.
Okay. Do you have any other questions?
No.
Okay. So it's clear. I think we're good.